Hello everyone, this video is about integration formula derivation. So this is called the proof of the fundamental theorem of calculus. To prove that for a continuous curve y equals f of x lying entirely above the x-axis for a axis between a and b, the area capital A of the region bounded by the curve, the x-axis and the vertical lines x equals a and x equals b is given by the integral from a to b of f of x dx. This is what we're trying to prove. So this area under this graph formula. So we start by defining capital A of x, which is the area bounded by x equals a and x equals some variable, the variables between a and b. So this is the capital A of x. Well, this depends on the value of x here. Now x, when the x equals a, when this variable x is a, what we get is nothing because it's just from a to a, which is 0. But when the x is b, we get the area we're trying to find, which is the integral from a to b. So this is called just a here, so it's just a. So what we need to prove is that the a of b is the integral from a to b of f of x dx, or the a of b is capital F of b minus capital F of a. The capital F means the integral, so after we integrate this small f, we get capital F. Capital F is the primitive of small f. So now we consider the region with the area a of x plus h, which is this a of x plus h is this area. So it's from a to x plus h. So this area minus a of x, so it's just this smaller area from a to x, so it's this area. So the shaded part in red is the a of x plus h minus a of x. So this is the shaded part in red. If we draw upper and lower rectangles of heights f of x plus h and f of x such that the shaded area is less than the area of the upper and greater than the lower. So here we want to find this area shaded in red, but now we use these rectangles. You see this green rectangle is, this is like the length or the base and the height of the blue rectangle, and for the blue and green rectangle here. So f of x means the value of y when the x is x. So when the value of x is this x here, what is the y value? Well, it's this length. So we get this height of the blue rectangle. And f of x plus h means the value of y when the x value is x plus h. So when this is x plus h, we get this height, or the height of the green rectangle. So hence we can write the area of the lower rectangle, so the area of the blue rectangle, which is, well, the height is x. We know that the height is x here. This is the f of x, the height, and this length here is from x to x plus h. So this length is actually h. So it's h times f of x for the blue, and for the green times f of x plus h. So actually this is plus h, so this is wrong actually. So I mean plus h plus h plus h plus h plus h. So the red shaded part is between blue and green shade green rectangles. And if we divide throughout the inequality by h, we get f of x is between this red shaded area and divided by h, and this divided by h is just the f of x plus h. And if we take the limit as h approaches 0 of everything, so in the middle we get the a prime of x using the definition of differentiation from the first principle, remember? And the area we're trying to find, because you know this is the same as this actually, so what we get is the f of x, because as h approaches 0, you see there's no h, so this is just f of x, and h approaches 0, this is just f of x, so it's exactly the same. So this whole thing is the same as f of x. So the a prime of x is the same as f of x, and when we integrate both sides, the integral of a prime is just a, the integral of f of x small becomes big, so this is the symbol for the integral, capital F of x, plus c. Now we're finding the c using, we know that the a of small a is 0 previously, so we get 0 for a of small a equals f of small a plus c, so the c is minus f of small a. So this a of x is therefore f of x minus f of a, and if we find the area we want to find from the beginning, which is f of b, we plug in b, we get f of b minus f of a, which is what we need to prove here. So therefore the area we want to find is the integral from a to b of f of x dx. Now for the volume of solids of revolution, so here the blue area under the curve is rotated 360 degrees about the x-axis. So this is like a cylinder. The volume of the cylinder is pi r squared h, and this is called the elemental volume. So we split this area we want, this volume we want to find, we split this volume into tiny layers of cylinders, so thin cylinders. So the volume of each thin small cylinders is called the elemental volume dV, which is pi y squared dx, because you see the height of the cylinder is dx, the elemental length, so this is infinitesimal x, the x is really small, infinitely small, and the radius is y, because the radius of the cylinder depends on the position of x. If the x is here, the radius is y. If the x is over here, the y is like bigger around here. So if we integrate both sides, we get the volume, which is the integral of everything on the right. Pi is a constant, so we can move it out. So pi integral y squared dx. Right, that's it. I'll see you again next time.